All right, so let's get started. So we were talking about linear classifiers. So this picture, everything on this slide, this applies no matter how you train it. So we haven't talked about whether we're training these with logistic regression or any other method. This is just anytime you have linear classification, what we do, we come up with a weight and bias. We use those to make a linear score, z. And then based on the sign of z or some other thresholding of z, we decide what the label is. So that's just sort of a generic method. And on this page, we're trying to understand a few things about that generic linear classification method. So the first thing we noticed last time is that this is the hyperplane that is, splitting one side from the other side. So in this case, our training data is here, red, here, blue, and we place the boundary here, and that means during test time, whenever we have a sample over here, we would say it's from the red class, or whenever we have a sample on the other side of the boundary, we say it's from the blue class. So this boundary, we proved to ourselves last time that this is orthogonal to the W vector. So that's sort of an interesting thing. Another interesting thing is, let's take a look at the intercepts of the boundary. So you notice that they have a very particular form. So when you're on the x2 axis, the intercept is minus b over w2. When you're on the x1 axis, it's minus b over w1. So right from there, like if I told you what b and w were on a test or homework, you can immediately draw the boundary, right? You figure out what the intercepts are and you connect the dots. So that's another interesting thing. So let's just try to understand, why that is. It's just because when you're on this axis, that means x1 is non-zero, but all the other x variables like x2 are zero, right? And so what happens is, if I set all the variables in this vector except x1 to 0, then I get b equals x1 w1. And then when I solve for x1, I get that x1 is minus b over w1. Okay, so that's why we get this. And you could do a similar thing here. When you're on this axis, x2 is non-zero, but all the other x variables are 0. You solve for x2 according to this equation, and you get this intercept. So does that make sense? Okay. So that's a couple things. Now, last time we were talking about how the method in this unit is based on the idea that we want to pay attention to the samples that are close to the boundary, the training samples close to the boundary, which are the difficult ones to classify, and the ones that are far from the boundary, and let's say on the correct side of the boundary, these are actually the easy ones to classify, so maybe we shouldn't pay too much attention to those. So that tells us, okay, we need to be able to understand how far any given point is from the boundary. So that's what we're going to talk about. We're going to talk about the signed distance from a point xi to the hyperplane. We're going to call it gamma I. And let's see how we're going to figure out what gamma I is. So here in this picture, we can see a point xi. We want to know how far xi is from this boundary. So if we're measuring the distance from a point to a line or a boundary, we need to measure the distance to the closest point on the line, right? We don't want to say that the distance from xi to the boundary is like here. So it's to the closest point on the boundary. But also we just learned that the boundary is perpendicular to w, so if I want to find the closest point to xi on the boundary, I should move in a direction that is parallel to w, or maybe in this case I'm moving in minus w over the norm of w. So this is just the unit vector in the w direction. This would be minus that. And here you can see gamma I, which I said is the distance. Gamma I is now going to be the norm of this vector. It's how much do I move in this direction until I'm at the boundary. Does that make sense how we're defining gamma I? It's just how far do I have to move in the proper direction until I'm on the boundary? That is the distance to the boundary. Okay, so to figure out that, all I need to do is I just need to plug in, so this is the point after we've moved, xi minus gamma I times w over its norm. I just plug that in for this x here, and then I solve for 0. So that's what we have down here. We plugged in the point on the boundary. We know that because it's on the boundary, in that equation, it must give us 0. And other than that, we just have to do a little rearranging. So we can see that this is b plus xi transpose w. So here's the xi transpose w. And then this last term, we have w transpose w. How can we express that using a norm? Norm squared, right? So that's the norm squared divided by the norm gives me just the norm itself without the square times minus gamma I. Okay, so we know 0 equals this. So if I want to figure out what gamma I is, I can just rearrange this. I can bring this gamma I term to the other side, divide by the norm of w, and this is the distance. Now, this is a little bit of a strange distance because it's a signed distance. Usually when we measure distance, it's always a non-negative quantity. In this case, it's important to know whether, what side of the boundary we're on. Are we on the red side of the boundary or are we on the blue side of the boundary? So this distance will be positive if you're on one side. I believe if you're on the y equals 1 side, this should be positive. And if you're on the blue side or the y not equals 1 side, this distance will be negative. So just be aware that it has a sign on it, and that's telling us which side of the boundary, one or not one, we're going to be on. Okay. So is everybody good with that idea? Okay, so we have a signed distance. And one last point, and you might notice this already from the way that the intercepts look, and we had a homework problem on this too in the last unit. If you scale both the bias and the weight by the same number alpha, what changes about the boundary? Does anything change? Like if you would plot the boundary corresponding to this, where would the intercepts be?
Alpha times b.
As far as alpha is positive, it shouldn't change.
Shouldn't change, right? Because the alpha will cancel top and bottom. So basically, this scale classifier gives you exactly the same boundary, and therefore we say that it's equivalent to the original classifier. Now, we want to make sure that alpha is positive, because if we make alpha negative, what's going to happen is this will change the sign on the distance. So let's just keep the sign on the distance the same so that positive is here, negative is here. But other than that, if you scale this classifier by alpha, it really doesn't change. What would change is the value of the score will change, but the sign of the score won't change. Exactly where the line is, none of that will change. Okay, so those are the main things. So all these things are important. We're going to use everything, but that's just sort of main points about hyperplane geometry that we can notice now, and they're going to be useful going forward. Okay, any questions on anything? All right. So another thing we talked about briefly back in Unit 5 was this notion of linear separability. And this is really a statement about the training data itself. So let's just say that the training data, again, is binary, and we're gonna assume for the purposes of this page that it's going to be binary plus minus 1, which is just for mathematical convenience. So we say that this training data is linearly separable, as shown here on the right, if you can always find a boundary that cleanly separates the training data into samples from one class and samples from the other class. That's what it means in words to be linearly separable. And as you can see here, when data is linearly separable, it usually means there's many boundaries that you can choose that are all going to cleanly separate it like that. So our goal on this page is to formulate this in a mathematical framework, try to get a nice, concise expression for what it means to be linearly separable. So to start out, notice that this quantity is the score, b plus, or the score on sample I. So we can say that linearly, for the data set to be linearly separable, it means that whenever the label is 1, the score zi is going to be greater or equal to some positive number epsilon. And whenever the label is -1, the score zi is less than or equal to some epsilon. So that would happen over here, like, this would maybe positive scores are this way, negative scores are this way. And this is just one way to define linearly separable. Okay, so positive, right here. Positive scores this way, and negative scores the other way. Okay. Are there any questions on this here, or is this making sense? Our next job is just to simplify this because it's really kind of clunky. There's multiple statements, there's all this stuff going on. So the first thing we can do is we can actually combine both of these into a single statement, leveraging the fact that y is either plus or minus 1. So in particular, when y is -1, if I multiply both sides of this equation by yi, then because yi is -1, it's going to change the sign of the inequality. It's going to turn it into that. It's going to change the sign here, and I'm just going to have yi on the left. Right? But if I do that on the top, then because yi is just 1, nothing really happens. So as a result, I get two expressions that look very similar, and in fact, they both look exactly like this. So this is a simpler way to write those two inequalities together as one that works when we have plus minus 1 labels. Okay, so this is our new statement of linear separability. But actually, we can simplify this as well, because we have this sort of annoying constant epsilon. Why does our definition really need to depend on epsilon? So to see that, let's divide both sides of the inequality by epsilon. Since it's positive, it won't change the sign. And so we're going to can write it like that. And now we essentially have a statement with a scaled B, scaled bias, and a scaled W. And we said, you know what, scaling doesn't actually change the classifier. We can scale or not scale, and it's equivalent. So that basically means let's just forget about the division by epsilon and write this more cleanly without it. Okay, so that's finally what we get. So to summarize, when we say that a data set is linearly separable, it means that there exists, this backward E means there exists some B and W such that for all training samples I, this equality holds. In short, yi times zi should be greater or equal to 1. Another way to think about this is a sign correction on the score. So remember that we're saying sometimes the score is positive if you're on one side, it's negative if you're on the other side. But once you multiply the score by yi, it should always be positive, right? At least you hope it is. If it is, then your training data is linearly separable. So this yi times zi is something that shows up a lot, and you can think about it as a sign-corrected score, if you like. I'll write that down. So basically, the sign-corrected score is something we hope it's as large as possible, and we're in great shape if it is greater or equal to 1. If you can find a B and W such that this is greater or equal to 1 for all your training samples, in that case, you have a linearly separable data set. Okay. All right, so we're getting close to putting this together. Are there any questions on this last part? Okay. So let's combine this statement with the one on the previous page, this one, to see what that means about gamma I. So in particular, what we can do is, I'll just do it over here. Imagine that I multiply both sides over here by yi. And notice that I have over here, this is this sign corrected score. So if I have linearly separable data, we know that this is greater or equal to 1. So that means that yi gamma I, which is the left side of above, is greater or equal to 1 over the norm of W. So this is, we can think of this as the sign corrected distance. Sign corrected distance from training sample xi to the boundary. Okay. So whenever that distance is positive, it means that the sample is on the good side of the boundary. It's going to be correctly classified. If the sign corrected distance was negative, it means it's actually on the wrong side of the boundary. It would be misclassified. In this linearly separable case, that's not going to happen. When the data is linearly separable, it means that that the sign corrected distance for all your training samples can be made greater than this 1 over norm W. And this is something that comes up a lot, so we're going to give it a name. We're going to call it gamma without any subscript, and we're going to call it the margin. Okay, so the margin is basically, from here, it's a lower bound on the minimum distance from any training sample to the boundary. So like the picture on the right, we have some training samples on this side. If you measure their distances to the boundary, and these are not signed distances, just distance as we, measure it, you would find that, that for all points, it's greater or equal to 1 over norm of W. So that's what this dotted line is showing you. This is gamma here, is the distance to the boundary. For all these training samples, they're at least 1 over W or gamma away from the boundary. Now when you go to the other side and you have these training samples, it's the same thing. On this side, they are at least 1 over norm of W or at least gamma from the boundary. Okay. So that's what's happening here. There's what we call this, is we sometimes call this the street. It's like you can make a street where your boundary is the center line and all your training samples are outside the street. That's what happens when the data is linearly separable. Now, in some cases, the street could be narrow, could be wide, but you can always make a little street there. A little zone around the boundary with no training samples in it. And where the training samples are all on the correct side of the boundary. That's what happens when the data is linearly separable. So, all right, so it's kind of making sense? So what happens now when I tilt the boundary away from how it's shown down here? If I tilt it clockwise, what happens to the width of my street? Gets narrower, exactly. So like if I have it over here, if I have it over here, now, actually let me move it a little bit. So if I have it over here, now you can see it's gotten pretty narrow, right? Or if I move it over here counterclockwise, then same thing. Got pretty narrow. So how do I make the street the widest? Yeah, or just like qualitatively based on this picture, how do I make it the widest?
Maximizing true gamma.
Yeah, exactly. I try to make whatever this is, gamma or 2 gamma, I try to make that as large as possible. I can see that as I tilt it, it becomes less, as it becomes narrower, I have a smaller gamma. So this is sort of the idea, at least the first idea of what we're going to try to do in this unit. We're going to try to make this street as wide as possible. And what's the motivation for that? Why do we want it to be wide?
To use other one real close to the bone.
Yeah, so,
Have good discrimination so that some samples are very far from our classifying one.
yeah. I think about it, like, when it comes to, for training data, everything's fine, right? It's already separable, so any boundary will work equally well. But for test data, we don't know that the test data will be as friendly as the training data. We could have test data that are here and maybe some squares here. And so because they're closer to the boundary, we're going to have to be, the more robustness, the farther the separation from the training to the boundary, the more likely that the test samples won't cross the boundary. So it's sort of like a matter of robustness. We have this training set, but we want our unknown test set to also behave well. So we're trying to put as much space between our training samples and our boundary. Okay, so yeah, and as was correctly noted, the way we're going to do this is we're going to maximize the margin. So that's the main idea. And concretely, the margin is gamma, or 1 over the norm of W. So maximizing that would be equivalent to minimizing the norm of W, right? Or the norm squared. If I minimize the norm, I minimize the norm squared, same thing. Of course, what's really important, though, in doing this is we have to make sure that we keep things linearly separable. As soon as you move your boundary so that it's not linearly separable, you're going to have some points on the wrong side of the boundary, and at that point, you don't necessarily want to minimize this. But as long as your boundary is linearly separating your data, in other words, your boundary is somewhere in here, in the middle, the way that you're going to maximize it is you're going to rotate it and shift it so that it's in that perfect spot. Okay, so when you solve this optimization problem, you can see it's a constrained optimization problem. We want to minimize this subject to this inequality constraint. Actually, there's n different inequality constraints. Once we solve this problem, we will get that boundary in exactly the right spot. So that's what these methods are based on. To say it in words, of all the B and the W that satisfy this linear separability constraint, the one with the widest street is going to be the one with the smallest norm of W squared. And that's going to be right here. Okay, so is this making sense? Any questions on that? Okay, it's actually a little bit tricky, so, but essentially, yeah, this is what we want to do. And when you look closely at, what is determining the boundary, like in this picture here, it's really determined completely by these 3 samples, right? None of these other samples here are telling us where to put the boundary. It's only down to these 3. They're completely determining where that boundary is. So that comes back to this sort of motivating idea that we suggested when we were looking at the performance of logistic regression in the MNIST data set, and we saw that it was somehow using all the training samples in a weird way to get what seemed like some overfitted W matrices. And we said, well, maybe what we should do is focus on the samples that were the hardest to classify rather than all the samples. And that's exactly what we're doing here. We're focusing on those 3 most difficult samples to classify, determining the boundary based on them, and not getting distracted by the easy ones. Just basically forgetting those. So that's kind of, we're putting everything together. And these specific points, the ones that determine the boundary, these are called the support vectors. That's the name they have. And it's just going to be some subset of your training data. the ones you're going to pay attention to. The rest, essentially, you're going to ignore. Okay, any questions? Yeah,
This assumes linear separability, right?
exactly. That's the problem, is that it requires, to even formulate this problem, it requires that your data is linearly separable. Because it's not, if it's not, and there's no way to solve this, there's no way to solve, or no way to satisfy these constraints, then there's no way to even solve the problem. Right? So it's a big problem. So this is sort of the first in a chain of ideas that will get a little bit more complicated, but at least in the linearly separable case, this one makes sense. So our next goal will be to generalize this so that it works even when the data is not linearly separable. Before we move on, though, are there any other questions? Good? Okay. All right, so, so to handle data that is not linearly separable, we're going to replace our constraint with a cost. So this is the constraint we know is for linear separability. So we can change this a little bit. Let's just move this to the right side of the inequality. So equivalently, we have this, right? So what we're going to do is rather than forcing this to be true, we're going to write it as a cost such that when this is true, the cost will go to 0. But if it's not true, the cost will increase. And then when we solve the optimization problem, we're going to add this cost to our original cost. And hopefully by making this 0, we can enforce linear separability if it's possible. So that's the goal. So how do we turn this into a cost? Well, so let's take a look at this. So, okay, when this is linearly separable, this term is at most 0. Could be negative or could be 0, but no bigger, right? So our cost is going to take the maximum of either 0 or this term. So you can see that in the good situation, that's linearly separable, we said that this is 0 or negative. And so when I take the max of 0 and something that's 0 or negative, I get 0. So that's great. If things are linearly separable, you can, if by forcing this cost to 0, you will enforce linear separability. That's great. But if things are not linearly separable, it's okay. You can still use this cost. You will never be able to force it all the way to 0, but that's fine. You can still make it, as small as it could be or as small as you want. And it allows you to extend our idea beyond this strict case of linear separability to non-linearly separable data sets, which are most of the ones we encounter in practice. So that's the idea, is that we have our old term here, and now instead of the inequality constraint, we have this cost. But we have this important parameter, C, that we're going to use to balance the two terms. It's going to be some positive constant. Before we talk about it, are there any questions about how we turn this into the cost? Yeah.
Yeah, what about the 0 and the 1?
Can you rephrase your question?
The 0, 1 within the...
Yeah. So this is max of either this or this. So you get two numbers and you pick the maximum. That's what we mean. Okay. And notice we're doing this for each eye. For each eye, you do a comparison between these two and you pick the maximum. That's what the cost is doing. Okay. So we have, this is our new optimization problem. This is an unconstrained problem. But we have this parameter C. So the reason we need this parameter here is we need to balance between how seriously we take this part and how seriously we take this. So you can imagine if I make C very large, then what that will do is it will focus on making, when we solve this problem, it will focus on making this part small, and it won't really care as much about this part because it's so highly weighted. On the other hand, if we make C really small, that essentially says, let's focus on minimizing this term and not worry too much about increasing that term. So there's sort of a trade-off here. By choosing C, you will fundamentally change the solutions that you get. Okay. So here again, larger C penalizes the violations. So by violations, we mean anytime this term is greater than 0, that's a violation of the margin. It basically means that for a fixed margin, let's say that a sample would be here or here or here if it should be on this side. So this is essentially non-zero if there's these violations, and larger C penalizes the violations more, and it basically penalizes this less. So if the norm of W is not as small, that means the margin is not as wide, right? So basically the street gets narrower. Larger C means narrower street. Smaller C means wider street. You can choose this directly. Let's look at some pictures. So here's 3 versions of C, 1,000, 10, and 0.1. So when C is large, we said it really wants to avoid any violations in the margin. It doesn't want to have any misclassified points or any points inside the street. And that's pretty much what's happening here. It's hard to tell maybe whether this is being misclassified or not, but it looks like maybe no points are being misclassified, or at least maybe 1 at the most. And the circled ones are the support vectors, so you can see that the street width is pretty small. Now, if we reduce C by 2 orders of magnitude, what happens is the street gets wider, and now any red samples that are on this side of the boundary are going to be counted as support vectors. Any blue samples that are on that side in the street or on the wrong side of the street, those are going to be support vectors. And you can see, you have a lot more support vectors now. Also, some of them are actually being misclassified, which was not happening over here. So by making C smaller, you're saying, I don't care as much about making this term small. I'm going to allow some bad things to happen, but I really want to make my street as wide as possible. And as you can see, you're able to make it wider. Now, if you make C even 2 orders of magnitude smaller, then your street gets very wide, and you have even more misclassified points. But that's sort of a trade-off that we need to choose. It's a regularization parameter, like we always have to choose. With lasso or ridge or all these techniques involve some sort of regularization parameter. And the nice thing is, like always, we can interpret this in terms of bias and variance. So when we have a large C, let's think about what happens. We have this very, very narrow street, and there's just a few support vectors. In this case, there's just a handful. I don't know, maybe like 8 or something like that. So that means that if you imagine running this experiment a number of times with different randomly generated data, every time your boundary would be changing quite a bit, right? Because it's only dependent on a few randomly generated samples. So it's going to be changing quite a bit. That means high variance. Variance is like all the variations you get across different experiments. So high variance, but it's low bias in the sense that your boundary is really doing a good job of classifying your test data. It's not making many mistakes. On the other hand, when you have small c, you have high bias, meaning there's structural errors. It's simply getting it wrong on a lot of the training data, but it's low variance. And it's low variance in the sense that the boundary is now sort of some sort of average, you could say, of all those many, many training samples. And if I did this experiment over and over again, the locations of the training samples would change, but their average wouldn't change as much. So you'd have a lot less variation across all those different experiments. So this is high bias, low variance. Low bias, high variance. The optimal one is something that we would need cross-validation to determine, but we can do that. We know how to do that.
Sorry, Professor, I didn't get the high variance concept or low variance.
So if you imagine that this is randomly generated training data according to some model, and I just run this random generation, I run this experiment many times. Every time I'm going to have a different pattern of points, and I'm going to have a different boundary, and my boundary is only going to be determined based on a very few random points, and so it's going to move quite a bit, because the closest points will be changing a lot. On the other hand, when I look over here, the boundary is really sort of the average of many points, which won't change that much from experiment to experiment. So low variance here, high variance here. Okay, so another important thing to know is that if I make C large enough, that means it will take this seriously enough that it will eventually push it to 0 if it's possible to push it to 0. In other words, if your training data is linearly separable, then it is possible to get this all the way to 0 with the right choice of the boundary. And that will happen once C is large enough. Now, if you make C very small, you may not have a boundary that linearly separates your data, and this may not be the same as our first idea here, the hard margin classifier. I can't remember if I said that, but this is what we call this hard margin classifier. This new idea is what we call the soft margin classifier, or also the support vector classifier. So the point here is that if C is large enough, you will get an agreement between the soft margin classifier and the hard margin classifier if they can agree, if your data is linearly separable. So that's sort of just to show you that really this is a direct extension of what we did earlier, but just more capable. It can handle non-linearly separable data as well. Okay, so sufficiently large C, this becomes equivalent to the other approach. Okay. All right, so yeah, these are kind of the main ideas. Another important thing is increasing C beyond a certain high value will have no effect. You will eventually make this as small as it can be. So if your training data is linearly separable, you will squash that all the way to 0, and further increasing C will have no effect on your design. It will just stay the same. So for a given data set, like a practical data set, it's going to have a minimum number of support vectors. Whatever the number is, you probably can't reduce it. It's just that the data is overlapping. It's impossible to come up with a linear boundary such that the data is linearly separated. So if you're playing around with different values of C and you keep increasing C and all of a sudden it just doesn't change after that, that's exactly what you should expect. Okay. All right, so yeah, any other questions so far?
Are we supposed to constrain the C as low as possible in practice use? Because if it increased variance, we can regard it as an overfitting.
Right. So remember, there's the bias variance trade-off. So we don't want our variance to be too large, but we also don't want our bias to be too large. So that's, if I go in one direction, if I go this way, small c, I get low variance, which I like, but my bias gets very large, which I don't like. If I go too far this direction, I have low bias, which I like, but high variance. So I don't want either of those. I want something in the middle, and the way to figure that out is cross-validation. All right. Good. Any other questions? All right. So another nice thing we can do is we can compare this directly to logistic loss, understand how it's different. And we can do that just by taking this equation and realizing that we can move this C over here. And it's exactly the same optimization problem, right? If I minimize this quantity, that's the same thing as minimizing this divided by C. So I can put my C here, or I can put it over here next to the 2. And once I do that, this is what we get for the problem, written that way. And we can compare it directly to L2 regularized logistic regression because it also has same form. Here's the ridge term. This is the penalty parameter we always choose for logistic regression. And here's logistic loss that we derived back in Unit 5. And we can actually make a direct comparison between this and this. This one, and now when we're working on the SVC, this is called the hinge loss. That's what it's called. And we can plot them. So this is plotted versus YIZI. That's the sign-corrected score, YIZI. Okay, so the hinge loss is in blue, and the logistic loss is in red. And you can see that at a high level, they're doing very similar things. They both have asymptotically a slope of 1 when you get over here, and they seem to have sort of a break point around here, and then as you go to the right, they're small. So the difference is really in the fact that the hinge loss goes exactly to 0 and stays at 0 for all those points, which means anytime your sign-corrected score is greater than 1, your hinge loss is perfectly happy. It says 0, no cost. Whereas your logistic loss, even on these points which are easy to classify, is still adding to your loss a little bit. Not by very much, but it's still there. And even if you go asymptotically, or as far as you want to the right, this stays positive. So it's always, even samples that are very easy to classify, it's still adding them to the loss. It's still complaining about them in some sense. Whereas the hinge loss stops complaining as long as you're on the right side of the street. So this is the boundary of the street. This is the center of the street, because that's where the sign-corrected score is 0. This is the other side of the street. So as long as you're on the correct side of the street, it's totally happy. And as soon as you get in the street or beyond, it just increases linearly. Okay, so that's really the difference between logistic loss we derived back in Unit 5 and this new idea. Hinge loss places no penalty on samples obeying the margin. Logistic loss penalizes all samples, but other than that, they're not hugely different. All right. Is this making sense, this page? All right, any questions? Okay. All right, so maybe we can convince ourselves that, like using math, that the weight vector, the optimal weight vector that we compute by solving this problem really does involve only the support vectors, meaning it's not at all distracted by any samples that are not support vectors. So this page just has a little bit of analysis that helps with that and a few other things. So again, this is the problem, or this is the cost function, we'll call it JSVC, that we would like to minimize to train our weights and biases. And so one thing we learned is at a minimum, if you take the gradient, it should go to 0, right? At least wherever the gradient exists. So this is a gradient with respect to the bias, this is a gradient with respect to the weights, and these are the optimal solutions, W star, B star, that minimize this cost. Okay, so let's figure out how do we take the gradient of this kind of complicated expression with the maximum. So I guess the thing to realize is that if this term here is negative, then when I take the derivative of this term with respect to b, I get nothing, because when this is negative, the max completely ignores this. So it's going to have no gradient with respect to b. Right? And when this is negative, that means that yi, so the yi-zi term must be greater than 1, right? When this is greater than 1, that's when this is negative, and that's when the 0 wins in the maximum. So that's this case here. Actually, sorry, that's this case here. So essentially, we're saying in that case, the gradient with respect to b should be 0. And so in this expression we derive, the alpha I term will make sure that that thing goes to 0. Now let's consider the other case. When this is positive, then we can forget about the maximum because the maximum will just pick this. And that's nice because then we're not distracted by this maximum term. And in that case, we can compute the gradient with respect to b pretty easily, right? It's just going to be c times minus yi. So here's the minus c yi. And this alpha I, in this case, we're going to set it to 1. So alpha I is like a switching variable. Whenever this term wins, then we're setting alpha I to 1. Whenever that term loses in the max, we're setting alpha I to 0. And that way we can write the gradient with a common expression. Now there is kind of a tricky point, which is when this is right exactly at 0. And it's not really clear what's going to happen there because essentially it's like you have something where you have a point that's not differentiable, and if you look at the slope coming from one direction, it's different than the slope coming from the other direction. So right at that point, there is no slope. And that's what happens when you try to take the gradient with respect to b, and this term is exactly 0. So to represent that case, we're just going to say, we don't really know how to even define the gradient at that point. We're just going to put a question mark there. And that's good enough for the purposes of this course. There are some more sophisticated ways to deal with this, but for us, we're just going to represent that as question mark, not really sure what happens there. Okay, but basically it could be non-zero, what happens there. Okay, so that's essentially the gradient with respect to b. Is everybody okay with this stuff? Yeah.
And that alpha, does it show up through the gradient from max?
So the alpha is kind of like a switching variable that allows us to either ignore the max, which is what we can do when this is greater than 0, or when this is less than 0, it basically says like this whole thing is gone, so there's no gradient with respect to b at all.
Right, so is that alpha something that we put in there, or is that something that you would derive from actually being able to?
Oh, if you knew the value of zi and yi, you would know what it is. So actually, I mean, this is going to be at the optimal solutions. So because we're taking the derivative at the optimal solution, that's where it'll be equal to 0. So if you knew these things and you know your training data, yes, you can compute alpha I for all the different i's. Okay, so it turns out that for the gradient with respect to w is it's all the same except when you take the gradient, instead of getting like, here gradient of this b is 1, gradient of this term with respect to w would be xi. So the expression is the same here except you have an xi. And then you have this term, so gradient of that with respect to w is just w itself. Okay, so that's where you can get these two equations. And from the second one, if you just rearrange this, so this equals 0 means that w star must have this form. And immediately you can now see that for all the alpha i's that are 0, all of these points, there's no contribution of those training samples to w star. So in fact, yes, those are the things that are not the support vectors. And all of these other things, points that are on the boundary or on the wrong side of the boundary, they contribute to w star. So here you can see equation for w star depends only on the support vectors, which are the xi, such that this inequality holds. Okay, so that's one way we'll use this little formulation here. You put a little box around it. I guess we have two results. Okay. And
Professor,
yes,
where did we get the second result from?
where do we get the second what?
The result, the summation.
Oh, just from this. So if this holds, I can multiply both sides by 1 over c, right? And then this holds. Okay. Let me skip ahead 2 slides, because I think it makes a little more sense this way. So here's the equation we just derived. So this is the W star based on the training data. And here is what we would do if we wanted to apply the SVC to test data. We'd be given a test vector x that's probably not in our training set. We need to compute the corresponding score given our trained parameters. And notice what happens. To compute that score, we're again using effectively we're only using the training samples that are the support vectors. So any non-support vectors will not affect our test score either. So so what we did here is I just plugged that into here to get this expression. So what's interesting here is you can see that one way to think about computing the score is you make a comparison between your test vector and all of your training samples, or at least all of the training samples that are going to matter, the support vectors. So it's a weighted linear combination of the inner products between x, the test vector, and each one of your support vectors. So that's, again, we see the SVC is focusing on what's most important when making a decision. It's not getting distracted by all the easy training samples. It's just focusing on the ones that are the difficult ones. Okay. We're getting almost to the end. So if you looked up the Wikipedia page for this stuff, which is actually pretty nicely written, you would notice that it's written in just a slightly different way. It's written in terms of these things called slack variables, and I thought it would be a good idea to explain it just so that if you do see this, in a book or something, you're comfortable with it. So all they're going to do in this notation is they're going to take this quantity, which we saw a lot of, and they're going to replace that with xi I. So in other words, in this equation here, they're just replacing this with the term xi I. So they have a sum, c times the sum over I xi I. Okay, so that's where c times the sum over I xi I. And then here's the other term that we had also over here. Okay, but now we have to make sure that we're treating this xi I correctly. So the first thing you notice is xi I must be non-negative, right? Can never be negative because it's the max of 0 and something else. So in this formulation, you have to write one inequality constraint is such that all the xi i's are positive. And the other thing is not only must xi I be greater than 0, or greater or equal to 0, but it also must be greater or equal to this. Right? So there's actually these two inequality constraints. But my point is this is just a different way of writing this. They're equivalent, just different ways of writing it. And there are a lot of books and so on that write it this way. There's a nice interpretation of these slack variables. It's just they're measuring what I would call violation of the margin. So let's say we're in this blue class. So this is the good place to be over here, right? If you're over here, then the xi I will be 0. So xi I equals 0 means sample is outside the street on the correct side of the hyperplane. Now, for xi I that's right on the boundary, or anywhere between here and here, it's going to be, starts to be like 0, goes up to 1, to 2, and then xi I can be even greater than 2 as this point moves farther and farther on the wrong side of the street. So this is just, these things are measuring directly how far each training sample is away from this good side of the street, if you will. So xi equals 0 means outside the street on the good side. 0 to 2 means in the street. And anything greater than 1 would mean over here, that means it's actually going to get misclassified, because this is the classification boundary. But for our training, any xi greater than 0 is considered a violation. So anything here. Okay. So that's the SVC. Next time we can talk briefly about a multi-class formulation, about how to apply it, and then we'll talk about, we'll see how well it works, and we'll talk about a way to significantly improve things that will inspire us and lead us on the path to deep learning. Okay, but I'll save that for next week. Stay safe. I haven't heard any tornado sounds outside, so hopefully it's over. I'll see you guys. Have a